ಸರ್ ಶುರು ಮಾಡೋದಾ ಸರ್? ನವೀನ್ ಸರ್.
Yes, sir.
ಸ್ಟಾರ್ಟ್ ಮಾಡೋದಾ ಸರ್?
Yes, sir. Yes, sir.
ಸೊ ಎಲ್ಲರಿಗೂ ನಮಸ್ಕಾರಗಳು. ಗುಡ್ ಈವ್ನಿಂಗ್ ಟು ಆಲ್. ಸೊ ಇಂದಿನ ವಿದ್ಯಾರ್ಥಿ ಪ್ರತಿಭಾ ಶೋಧ ಯೋಜನೆಯ 68ನೇ ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮಕ್ಕೆ ನಮ್ಮ ಮಂಗಳೂರಿನ ಸೆಂಟ್ ಅಲೇಸ್ ಕಾಲೇಜಿನ ಪ್ರಾಧ್ಯಾಪಕರಾದಂತಹ ನವೀನ್ ಮಾಸ್ಕರೇನ್ಸ್ ಅವರನ್ನ ಸ್ವಾಗತಿಸ್ತಾ ಇದ್ದೀನಿ. ವೆಲ್ಕಮ್ ಟು ಯು ಸರ್.
Thank you, sir.
ಸೊ ಅದೇ ರೀತಿ ಇಂದಿನ ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮಕ್ಕೆ ಹಾಜರಾಗಿರುವ ನನ್ನ ಎಲ್ಲ ವಿದ್ಯಾರ್ಥಿ ಮಿತ್ರರು, ಅಧ್ಯಾಪಕರು, ಶಿಕ್ಷಕರು ಹಾಗೂ ನನ್ನ ಸಹೋದ್ಯೋಗಿಗಳನ್ನು ಕೂಡ ಈ ಒಂದು ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮಕ್ಕೆ ಸ್ವಾಗತಿಸುತ್ತಾ, ನಮ್ಮ ನವೀನ್ ಮಾಸ್ಕರೇನ್ಸ್ ರವರು ವಿದ್ಯಾರ್ಥಿ ಪ್ರತಿಭಾ ಶೋಧ ಯೋಜನೆಯಲ್ಲಿ ನಮ್ಮ ಪದವಿ ಪೂರ್ವ ವಿದ್ಯಾರ್ಥಿಗಳಿಗೆ ಹಲವಾರು ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮಗಳನ್ನು ನೀಡಿದ್ದು, ಅವರ ಬಗ್ಗೆ ಈಗಾಗಲೇ ನಾನು ಒಂದು ಕಿರು ಪರಿಚಯವನ್ನು ಮಾಡಿಕೊಟ್ಟಿದ್ದು, ಜೊತೆಗೆ ಕಾಲಾವಕಾಶವು ಕಡಿಮೆ ಇರೋದ್ರಿಂದ ಅವರನ್ನ ಈ ಒಂದು ವಿದ್ಯಾರ್ಥಿ ಪ್ರತಿಭಾ ಶೋಧ ಯೋಜನೆಯ ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮದ ವೇದಿಕೆಗೆ ನಾನು ಬರಮಾಡ್ಕೊತಾ ಇದ್ದೀನಿ. ಓವರ್ ಟು ಯು ಸರ್.
Thank you, sir. So, dear students, we are going to see this topic today. That is semiconductor electronics or semiconductor devices. First of all, let us try to understand the classification of solids. You all know this, I believe. Conductors, insulators, and semiconductors. Can anybody give me examples for semiconductors? Any examples for semiconductors? Can we use the chat box? Anybody knows any examples for semiconductors? No? No? Okay. So I'll give you silicon, germanium. Correct, no? These are all examples of semiconductors. Okay. When do we say, in the band gap theory of solids, when do we know that solids are semiconductors? If the band gap, that is Eg, if it is less than 3 eV, then we call it as semiconductors. If it is greater than 3 eV, it is referred as insulators. And if it is approximately 0 or closer to 0, then we call it as metals. Metals are very good conductors, is it not? There is no energy gap at all. Here, energy gap, when I say, you must be knowing that there are two bands in the band structure, the valence band and the conduction band. If there is no energy gap between the two, it is called conductor. If the energy gap is above 3 eV, it is insulator. If it is less than 3 eV, then it becomes semiconductor. Okay. So this is what we need to know initially. This number is very important. Okay, 3 eV, 3 eV. Correct. So to identify, that we are discussing semiconductors, we restrict our discussion in this session only on semiconductors. Okay. So what are the properties of semiconductors? You all must be knowing by now that semiconductors are tetravalent. What's the meaning of that? Valency is 4. Which are the examples I gave for semiconductors just now? Silicon, then germanium. We can try to find out how the valency is 4 by knowing its which number, atomic number. Is it not? What's the atomic number of Si? Anybody can put this in chat or unmute and speak. We write the electronic configuration based on atomic number. What's the atomic number for silicon? You're all good chemistry students, so you must be knowing, right? 14, no? 14. And of germanium it is 32. And if I ask you to write the electronic configuration for silicon, it will be 1s2, 2s2, 2p6, 3s2, and 3p2. Why I stopped at 2 here in p, though we know that its capacity is 6, right? You just count, add 2 plus 2 is 4, 4 plus 6 is 10, 10 plus 2 is 12, 12 plus which number will give you 14, which is the required number? Only 2, right? So I wrote 2. Now, how do I know that here the valency is 4? Look at this outermost orbit. Count the number of electrons. 2 plus 2 it is. So it's 4. Anybody would like to tell me, unmute and tell me the electronic configuration for this 32? 32? Is it possible? No? 1s2, 2s2, 2p6. Come on then. 3s2. Surely 3p6 because it is 32 now, not 14. Then 4s2. This is a crucial one. What I should write now? It's only not a SP subshell. It is also D, no? 3D10. Now count. 2 plus 2, 4, 4 plus 6, 10, 10 plus 2, 12, 12 plus 6, 18, 18 plus 2, 20, 20 plus 10, 30, and now 4p, 2. Now how the valency is 4 here again? Again 4 you see. 4 is the outermost orbit. And what are the number of electrons in this? 2 plus 2, 4. So I said semiconductors are tetravalent. And I have not written one important one here. They are crystalline in structure. They have crystalline structure. Correct, no? If at all, if I have to draw silicon, it will be something like this. 9 dots we always draw and others we draw, no? Crystalline structure. I can write +4 inside all and then covalent bonds, no? Because what is the valency of each? 4, right? So like this we draw, right? Nice picture we get. You all are familiar with this crystalline structure. So semiconductors are crystalline in structure and are tetravalent. The next point that I've written here. Semiconductors have negative temperature coefficient. So alpha is negative. We all know that for metals, conductors, the temperature coefficient was positive. Alpha is positive. Alpha is nearly 0 for very good materials like, from which standard resistances are made. But for semiconductors, alpha is negative. What's the meaning? As temperature increases, resistance will not increase. That means it's positive alpha if it increases. Resistance decreases. So that's the meaning of this. Why? Because as temperature increases, bonds are broken. And when a bond is broken when temperature increases. When a bond is broken in semiconductors, electron-hole pair is generated. Electron-hole pair is generated. So, and these are free electrons, no? So, free electrons, right? So, as the temperature increases, therefore, you find that, conductivity increases, which means resistivity decreases, resistance decreases. The only way we can increase the conductivity of a semiconductor is by increasing temperature right now. Then we know we can do it by adding impurities. That is called doping, no? So there are two ways in which I can increase the conductivity of a semiconductor. Which are those two ways? One is to increase the temperature. Other one is to add impurities. So these are the two methods by which we can increase the conductivity of a semiconductor. Okay. And then here I've written types. Which are the two types that we have in the semiconductors? Semiconductors types. We know that there are two types possible, no? Intrinsic and extrinsic. Pure semiconductors are called intrinsic semiconductors. And doped semiconductors, when you add impurities, it becomes extrinsic semiconductors. So this is type of semiconductors based on pure and impure impurity. We can also classify semiconductors based on number of elements which are present. As if there is only one element present, then it is elemental semiconductor. Example, silicon and germanium. They are elemental semiconductors. But in this chapter, we also know we have compound semiconductors like gallium arsenide, right? Gallium phosphide, gallium arsenide phosphide. These are all used in the construction of LEDs, light emitting diodes. What's the full form of LED? Light emitting diodes. Where we discuss even these compound semiconductors. So based on the type of elements present, number of elements present, we have elemental semiconductors and compound semiconductors. Based on the purity, we have intrinsic semiconductor and extrinsic semiconductor. So how to increase the conductivity of an intrinsic semiconductor? This is the picture which I have shown here down here. This is a picture of a intrinsic semiconductor. How to increase the conductivity of this? Two ways. One is to increase the temperature. Other one is to add impurities. Dope. That's called doping. Okay. By doping, we can always, increase the conductivity. It is like getting ready to or getting warmed up for a game. When you should not play any game without warming up. As we warm up, what happens? Our temperature increases, and therefore the conductivity of ours also will increase because we can play better, right? So that is one way of increasing the conductivity. Other one is to add dopants. That's what we do. Many times, some are taking the external help. They dope themselves to increase their conductivity, but that is not the right way actually. Correct? No. In games, I'm saying, but here that is the best way. In semiconductors, the best way of increasing the conductivity is to get doped, right? So by adding impurity atoms, we can increase the conductivity drastically, and that is extrinsic semiconductor. So if you know what are extrinsic semiconductors, they are nothing but doped semiconductors. So doped semiconductors are extrinsic. Okay. In intrinsic semiconductors, we can write one formula, right? N number of electrons and number of holes are always equal, and that is called Ni, let's say, intrinsic carrier concentration. Why they are equal? Because in intrinsic semiconductors, when the temperature increases, we don't dope in intrinsic, remember. When temperature increases, electron-hole pairs are formed. If 50 bonds are broken, 50 electrons are there, free electrons, 50 holes are there. Correct? Therefore, we say conductivity in intrinsic semiconductor is not only due to electrons, it is also due to holes. But contribution is equal. Correct? No? Conductivity in intrinsic semiconductor is due to both electrons as well as holes. What is hole? Anybody know what is a hole? What is a hole? Hole is an imaginary particle said to have positive charge, exists outside the nucleus only in semiconductors. I said so many things. Now, hole is a imaginary entity. Nobody has seen an electron. We can only feel for an electron. So just imagine, therefore, what is a hole? Hole is an imaginary entity said to have positive charge, surely, because electron can fill this vacancy. So therefore, it should have a positive charge. It is said to have a positive charge. It exists outside the nucleus. You all know it. It cannot be inside the nucleus. But only in semiconductors. Do we have holes in? I'm not talking about the physical holes that are present. Remember, these are the holes that we talk about only in semiconductors, right? Exists outside the nucleus. We don't have holes in conductors as well as insulators, right? So that is all about intrinsic semiconductors. This is a formula, N is equal to NH into Ni. But the same formula for extrinsic will be N E into NH will be equal to Ni square. Okay. The number of electrons and holes, when you multiply, it will be equal to Ni square. And what is Ni? Is the number of intrinsic carried concentration of a pure semiconductor. Okay. So this formula will hold good for extrinsic semiconductor, whether it is P-type semiconductor or N-type semiconductor. So there are two types of extrinsic semiconductors. What are extrinsic? I said doped semiconductors. No. So by choosing a proper dopant, we can make either P-type or N-type. Okay. By adding what is the valency of intrinsic semiconductors? Semiconductors tetravalent, you said. One valency less and one valency more. So by adding pentavalent, we get N-type semiconductors. Pentavalent like phosphorus and so on. We get N-type semiconductors. Similarly, by adding trivalent impurity atoms, trivalent means valency is 3, one less. We get P-type semiconductors. Like for example, gallium, aluminium, indium, all these are examples of P-type. For N-type, I said phosphorus, bismuth, arsenic, antimony, all these are N-type semiconductors. Here is a picture. See here. Remember in this picture, some things are missing. Which are the things which are missing? Silicon atoms are not shown. This what is shown is a pentavalent, let's say phosphorus ion, because it has donated one electron, because it had valency 5, no? To bond with silicon atoms, we require only 4. So the one which is free, okay, one which is fifth is available in the conduction band, easily at room temperature. That's how for every plus ion, phosphorus ion, we have one free electron. So these are all symbols of electron. So if there are 50 phosphorus atoms added, there will be 50 electrons. If we add 1000 phosphorus atoms, then there will be 1000 electrons at room temperature. And that's why we have now electrons in majority. Let's say due to temperature, this is due to doping, no? Due to temperature, let's say only 10, I'm taking only a small example. Don't think that it will be 1000 and all. It will be huge number. But to understand, it's easy. 10 bonds are broken, let's say. Then there will be 10 electrons and 10 holes, right? So altogether, how many electrons are there now? 50 plus 10, 60. But holes are only 10. So electron number will become more than the hole number. Or if you take 1000, 1000 plus 10 is 1010 totally. But the whole number is only 10. So who are in majority now? Electrons are in majority, holes are in minority in a N-type semiconductor. That's why the name N-type. N. These electrons are in majority. Electron majority. And what's the charge assumed for an electron always? Negative. That's why it's N-type. Don't think that the charge on N-type semiconductor is negative. So this is electrically neutral. Both N-type semiconductor as well as P-type semiconductors are electrically neutral. Why? Anybody would like to answer that question? Why N-type and P-type semiconductors are electrically neutral? Because to make N-type, we did not add electrons, or we never removed electrons. No, we added atoms. Which atoms we added? Pentavalent phosphorus atoms we added, let's say. And don't you think that phosphorus atoms are also electrically neutral? Correct, no? So there is no extra electron which has come anywhere to make it negatively charged. These electrons have come because, the phosphorus atom was not able to bond with all its electrons with the silicon. Silicon, what were the number of electrons available? Outermost, 4. Phosphorus, how many available? 5. Out of this 5, only 4 could bond with this. 1 was free. Correct, no? But this entire thing was of the phosphorus, right? So remember, we never added extra electrons. We added only atoms which were electrically neutral. Therefore, charge of N-type semiconductor is neutral. Charge of P-type is also neutral. There is a spelling mistake here. Type semiconductor N, semiconductor P. This is so similarly P now. If you are seeing P, imagine gallium. Gallium is having valency 3. What is the valency of silicon? 4. So there is one shortage now. What will happen? The shortage will be filled. Shortage will be a hole. If I have to show you the picture, I can show the picture maybe here. Let's say this is the +3 one. So only 3 are there here. There is absence here, no? So there are neighboring silicon atoms, right? This is gallium at the center. Let's say this electron at room temperature fills this. But it was inside the bond, no? The bond is broken here. When the bond is broken, definitely hole is also created there. Correct, no? So electron hole, that electron has filled here. That means this will become stable now. But since this gallium attracted one electron from the neighboring silicon, it becomes a negative ion. That's what is shown in this picture. See, every gallium atom which was added to make a P-type semiconductor becomes a negative ion, and it gives rise to one hole. And hole is set to a positive charge, therefore I am showing plus. Do you think that P-type semiconductor has only this? No, in addition to this, there will be electron hole pairs. Here also, electron hole pairs. And this is because of temperature, no? This is due to temperature. Somewhere it will be there. And also we can draw. So this is your N-type and P-type semiconductor. So now questions before we move further. Anybody answer? What is the charge of P-type semiconductor? What is the charge on P-type semiconductor? Nobody is answering. Positive, very good. Somebody has answered already, right? Swati, very nice. But is it positive? No. Charge on P-type semiconductor is no charge. Electrically neutral, you should say. Why? Because we added not electrons. We never removed also electrons. We added atoms, no. To make P-type semiconductors to silicon crystal, what did I add? Impurity atoms. Which impurity atoms? Trivalent. Like gallium, aluminium, indium. Correct now. So therefore, it is electrically neutral, not positive. So you need to get this one right. Okay, next question. How do I make a N-type semiconductor? This is easy. How do I make a N-type semiconductor from intrinsic semiconductor? Add pentavalent impurity atoms. Perfect, Swati. This time you're right. Correct. Add pentavalent impurity atoms to make a N-type semiconductor. Perfect. Good. Pentavalent impurity atoms like phosphorus, I said. Now here is a picture of a PN junction. Why this PN junction is so important? It was given by Russell Hall. People have forgotten his name. People remember some other names. Some other name is the inventor of a diode, remember. Of course, this PN junction itself becomes a diode later on. But the person who invented this PN junction is Russell Hall. Okay, he did a very good job of giving us a PN junction because P as it is or N as it is has no application. Application comes only when we have a PN junction. And the moment the PN junction is formed, PN junction is this. See, this is N type. This is P type. Again, you see this. This region from here to here, is it neutral? Yes. From here to here, is it neutral? The answer is again yes. Okay. Fine. But what is the answer to the charge of this region? Yeah, this side it is positive. See here, only positive it is. This side is negative. You can see also from the battery, lines here. Why? Because the moment the P and N were fused electrically, electrons which were present here combined with the holes which were present here. Therefore, they disappeared. Electrons and holes in that region got disappeared, leaving behind only the ions, positive ions here and negative ions here. That means a field was set up, electric field was set up, and that field was from positive to negative, this way. Electric field is set up. Okay. So try to understand, therefore. So this region is referred as space charge region because it is a charged region. Because these regions are not charged. And they prevent actually the further crossing over of electrons and holes. Why? Because negative doesn't get attracted by the positive potential which is there this side. Positive here. And the electrons which want to cross over this side are getting repelled by the negative potential which is there this side. Holes are also getting repelled. So therefore, a stable equilibrium stage is reached. All that we say, but try to understand there are two currents which we need to discuss here. And nobody, hardly you all give importance to all this, but I give importance to this. As we read from H.C. Verma, we will get to understand that these are the two currents what we need to know. So let me draw a P and very simple one, P and N. We know that this is full of electrons, N side, and this is full of holes. And the diffusion is because of the density gradients, no? This side is full of electrons, this side is less of electrons. This side is full of holes, this side is less of holes. So to balance, therefore, obviously the diffusion has to happen. Electrons should cross over this way and holes should cross over this way. And this give rise to a current which we know as diffusion current. Remember, current is always the direction in which the positive charge tends to move. And positive charge is always hole, not in the direction of holes, no, but opposite the direction of holes. Electron moves this way, but therefore the current direction should be opposite. Okay. And this is diffusion current. It is from P to N. What about drift? Drift current. Drift current is happening in this depletion region. You all know that this is space charge region, also called as depletion region. Why? In this region, no, there are no free electrons and holes. Even when they are created also, they are swept away, or the bonds are broken, means electron hole pairs are formed here, but they are swept away because of the electric field that exists. Just imagine electron hole pair forming here. There is an electric field here, no, which is from positive to negative. So electrons experience a force in a direction opposite to the field, and hole experiences a force in a direction along the field. So this hole moves this way, and electrons move in a direction opposite to the field, is what we know. Correct? No. So that gives rise to a current called drift current. That is happening in the depletion region. If I have to redraw this graph, let me erase this and redraw it for you once again with the Pn. Diffusion is very clear. It's because of the density gradient. The majority electrons are crossing over. And now this is again Pn. This is the depletion region that we have, in which the majority charge carriers, which are electrons here and which are holes here, are absent here, depleted off. Okay. So the moment the bonds are broken, the electrons and holes, they move in a direction which is not along the field but opposite to the field. So that gives rise to a current called diffusion current. So at equilibrium, when a p-n junction is said to be formed, when current due to diffusion must be equal to current due to drift. Current due to diffusion must be, current due to drift. Okay. So then only we say, please understand, in P side we have here like this, okay, acceptor ions, and here we had donor ions, and therefore this was N here and this is P here, remember. Similarly here also. So direction of electric field is this way. When a electron hole pair is generated here inside this, because of temperature, electron experiences a force not along the direction of the field but opposite to the field. That means it moves this way from P to N. Hole moves this way. Therefore, the direction of drift current is this. Direction of diffusion current was this, P to N. But this is N to P. This is P to N. Opposite, no, they are. So when they become equal in magnitude, the net current becomes zero, right? Net current is zero. And that's why we say a p-n junction is formed. So p-n junction is formed when the diffusion current is equal to the drift current. Diffusion current is due to the density gradient of electrons and holes. Electrons are rich here, holes are rich here. Correct? No. So the direction of diffusion is from here to here. Draw a big arrow if you want. This is diffusion current. Okay, but when electron hole pairs are formed here inside, hole, how it is moving? Direction of electric field is this. Same way, no, hole experiences a force along the direction of the field. So that is the direction of drift current now. This one. This is current due to drift. Are they in the same direction? No. But when a p-n junction is said to be formed, when current due to drift is equal to current due to diffusion. So now, before I proceed, question. Let's see who will answer now. Not able to see the chart. Okay. I don't know, something is stuck with my pen. Is it because of this diagram? Give me a minute. Doesn't matter. Not able to see, but okay. Somebody tell me, therefore, someone tell me now. Okay. What's the direction of diffusion current? And what's the direction of drift current? Now I'm able to see. Okay. Anybody can answer. Swati was answering so far. Let's see. Diffusion current direction. Diffusion is because of the majority charge carriers. Direction of electric field is this in the space charge region from positive to negative. When an electron hole pair is generated here, electron will move in a direction opposite to the field, but hole will move in a direction along the field. That means hole is moving from, remember this is N side, this is P side. So your drift current is from N to P, whereas your diffusion current is from P to N. Please don't forget this. You can't go wrong, you know. And when the PN junction is said to be formed, these two currents must be equal. These two currents must be equal. Okay. Fine. So good. So let's move to now the next topic, therefore. If there are no questions, let's see. The question is no. Biasing. Applying external voltage is called biasing actually. Applying external. We had internal voltage, we saw that, but the barrier potential was there. It is 0.6 EV, 6 volt for silicon, 0.6 to 0.7 for silicon, and for germanium diode and all, it becomes 0.3 volt or 0.2 or 0.3. Okay. Now, this is not that internal one. This is external. That is called biasing. How many ways we can bias a diode? What is diode actually now? This is a diode symbol. You all know it. Same PN junction, P and N, with electrodes, man. Anode and cathode. This is anode, this is cathode. This becomes a PN junction diode. That's called semiconductor diode because it's made up of semiconductor, no? And this diode has plenty of applications. You all know it. We can't think of the modern life without these semiconductor devices because we are living in a semiconductor world. You may say we are living in a chip world. The chip is all of semiconductors. And inside these chips, all we have are diodes and transistors is what we are studying in this, important stage. Second PUC physics. Apply an external voltage. So the way we apply, we have two bias, forward bias and reverse bias. When do we say a PN junction is forward bias? When the P is connected to positive of the external battery and N is connected to negative of the external battery. Anybody? Reverse bias now? Reverse bias? P is connected to negative and N is connected to positive. This is reverse bias. And the characteristics of this forward bias and reverse bias, it is given in always the first and the third quadrant in a graph sheet. Because this is positive voltage, this will be negative voltage, and that's what we know. If this is positive voltage, then definitely this is a negative voltage. And current direction also, not the same direction, you see. Here the current flows from, you all know how the current flows in electric current, they have taught you, from higher potential to lower potential. So in the semiconductor, it is from P to N, which means what we had now, very crucial this is, we had high diffusion and high drift current, no, inside the junction. Which one do you think they were equal? Which one do you think increases now drastically? Which one? Diffusion current after forward biasing. Whether diffusion and drift current remains the same or they change. They change, surely. Which one increases, which one decreases? Or decrease, it can remain the same also. Which one is affected? If you're able to answer in terms of diffusion and drift current, I think you have understood this biasing, to a greater extent. Not to the same extent as we all understand by reading the simple text. Remember, diffusion increases by a great percentage. Okay. And drift remains almost the same, because drift is due to the temperature, no, and electric field, right, which is there inside the space charge region, which is not affected much. The width of the depletion region has decreased only. Okay. But it's a slight change. So therefore, drift current, has decreased, or it remains almost the same, but diffusion increases drastically. And that's why now there is a net current, no? From where to diffusion was always from P to N, remember. And drift current is always from N to P. But this has remained almost the same or slightly decreased, but this has increased drastically. That's the direction of current that I'm showing here. Okay. So there's current here. What about here? In this, can we speak about diffusion and drift? Here, the diffusion is impossible. Diffusion is not increasing, it is actually decreasing. But here, this one is almost the same. Earlier it was, see, remember, these are in microamperes, this current, But when during forward bias, the current increased from microampere to milliampere. But here, now what is the net of this? Net will become still smaller than what was earlier drift. Means current will be very small, of the order of microamperes. And that's what we know in this characteristic. You should know that this y-axis here is in microampere and this is in milliampere. But these are both in volts. But one is positive potential, other one is negative potential. So this is what we get. In fact, of course, we don't get till here because this region is called breakdown region. Breakdown will kill the PN junction permanently. We cannot use it anymore. So we use it only till here, this voltage maybe. Maybe this itself is 30 volt, enough. Minus 30, surely. This is known as the cut-in voltage or knee voltage. And this voltage is what I wrote that time. 0.6 EV for silicon and 0.2 EV for germanium. If at all, if the base is germanium, then 0.2 you get. If the base was silicon and then you doped it, then it becomes 0.6 EV, this value. Knee voltage or cut-in voltage. Cut-in voltage is the forward voltage at which diode begins to conduct. See this one. Current is in milliamperes. This is the breakdown voltage at which the PN junction is spoiled. The voltage that is minus 50 is shown here. It's a reverse voltage, not the forward voltage at which junction breakdown takes place. Okay, so these are the characteristics. Application of diode. We use it for rectification. What is rectification? What is rectification according to you? Converting AC to pulsating DC, not perfect DC, pulsating DC. This is a pulse here. Can you see? This is pulsating. See here also pulsating. Of course, this is full wave rectification, and this one is half wave rectification. If the output current or voltage exists only for one half cycle, you are only for positive half cycle, the output is there. This is the input, no. This is the output. And we used a diode. Here one diode, here how many diodes are used? Two diodes are used. This is half wave rectifier, and this one is full wave rectifier. Correct? So converting AC to pulsating DC is what we refer as rectification. All right. So if at all, if they ask you how much DC is there in the output of half wave rectifier, the answer is, V0 by pi. And here how much is there, sir? 2V0 by pi. 2 times. So this is a better rectification, full wave rectifier, than half wave rectifier. Okay. Fine. Rectification is nothing but converting AC to pulsating DC, because most of our instrument, even your mobile charger and all, it wants only DC, no. But what we get in our house is AC. So there is a charger unit which converts that AC to DC. But what is that component which converts alternating current in two directions to only current flowing in one direction? That's a diode. Because diode conducts only when it is forward biased, and it doesn't conduct when it is reverse biased. That's a property that is made use of. So if at all, if you want to know which property of the diode converts AC to pulsating DC, it is a property that diode conducts only in this direction, no, the current. This way current flows? No. Of course, there is current called microamperes, but this current is in milliampere. What is microampere compared to milliampere? 1,000 times smaller. It is like 1 rupee and 1,000 rupees. Which is the money in this? 1,000 rupees is the money. 1 rupee is nothing in front of 1,000 rupees. If I distribute these two to two students in the class, the one who got 1 rupee will return it to me, because this person has got 1,000 rupees. You see, that's the difference between microampere and milliampere. Try to understand. Milliampere is nothing in front of milliampere. Microampere is nothing in front of milliampere. Therefore, this is not current at all. This is only due to minority charge carriers, whereas this one is due to majority charge carriers. Before I proceed to special diodes, if I ask you, can you distinguish between P-type and N-type semiconductor? What are the, two columns if I have to fill? How to get P-type? By doping with trivalent. One I will give you. This one, pentavalent. Any other differences you can think of? In P-type, who is greater, who is smaller? In terms of, mobile charge carriers. Free electrons and holes. Number of holes is greater than number of electrons here. That's why P-type. In N-type, number of electrons is much greater than number of holes. But of course, the formula is very clear. Ne into NH must be equal to Ni square. Ni is when it was not doped. What is the carrier concentration? Number of electrons and holes were equal, no? That's square. Ne into NH will be always equal to Ni square. Okay. Here, conductivity is mainly due to holes. Here, the conductivity is mainly due to electrons. Okay. And here, who are the majority charge carriers? Holes. Where are they? They are in the valence band. Holes are in valence band. Whereas who are the charge carriers here? Majority electrons. And where are they? They are in the conduction band. So this is the conduction band. This is the valence band. The donor impurity level will be closer to the conduction band of the pentavalent impurity atoms, whereas the acceptor level is closer to the valence band. Acceptor level. This is donor level. Donor level of pentavalent +5. This is of +3. Okay. So these are the differences that we all know. We should know of P-type and N-type. Now we need to discuss some special diodes: Zener, LED, photodiode, and solar cell. Now, this is the symbol of Zener. Many times I keep asking, what is this symbol? 2 lines like this. When you are saying that this is Z, no, sir. Zener starts with Z, the scientist who invented. No. This is how the characteristic curve will appear of the Zener. That's why like this. I have to draw again. See, this is our I and V. This is how the characteristic curve will be. Reverse bias. Zener diode conducts during reverse bias. That's a speciality of Zener. Whereas diode conducts only during forward bias. Zener diode conducts both during forward bias and reverse bias. And when it is specially used under reverse bias, and it is used as voltage regulator, getting a constant output voltage. So Zener is always used under reverse bias, means this is P type connected to negative and N type connected to positive. Output voltage across the Zener will be almost a constant, and which is equal to the Zener voltage called breakdown voltage. Yes, Zener is going to operate very safely in the breakdown region, but not the semiconductor diode. Zener diode is designed to operate in the breakdown region. What makes it so special, sir? Why it is made to operate in the Zener breakdown region, which is or ordinary diode is not capable of? Remember, Zener is heavily doped. Heavily doped. Not like our ordinary diode, which was moderately doped. Zener is heavily doped. That's the property which allows it to operate safely in the breakdown region. Its depletion region is thin compared to ordinary diode. Therefore, even a slight increase in the width of the depletion region, electric intensity increases drastically, and the bonds are broken, and therefore the current rises sharply. This is also in milliamperes. This is also in milliamperes. Whereas in ordinary diode, this was in microamperes. No. Zener conducts even during reverse bias. So name a diode which conducts in both the directions. If they ask you, none of these except only Zener. Okay. Zener is the only diode which can conduct both in forward bias as well as reverse bias. Light emitting diode. Among these three, LED, photo, and solar, similarities are these, or differences are these. This is the only one which converts electric energy to light energy, whereas these two convert light energy to electric energy, both photodiode as well as solar cell. LED converts electric energy to light energy. So to construct a LED, we cannot construct a LED with elemental semiconductors. We need to have a compound semiconductors, and the energy gap EG required is at least 1.8 EV. So this is one more number which you should remember. What is the energy gap of silicon? 1.1 EV. Is it enough? No, no, no. 1.8 minimum I need. I said no. What is the energy gap of germanium? 7 EV. Is that also enough? No. So we need therefore these compound semiconductors like gallium arsenide, whose energy gap will be 1.8 EV or above. 1.9 EV also will do. Yeah, but less than 3 EV. Those are all called semiconductors. No less than 3 EV. So this can be thought of as the light emitting diodes. Okay. And when the light is emitted, only when the diode is forward biased. But you need to make use of not element semiconductors, but compound semiconductors. Photodiode. Photodiode is again operated under reverse bias, like how Zener is also operated under reverse bias to get the very important applications called regulation. Even photodiode is also operated under reverse bias. Actually, under reverse bias, there is no current, no? But when light of suitable intensity and wavelength is impressed on the photodiode, P and N, there is a depletion, there is a glass window here. So light is made to fall. When the light is made to fall, more bonds are broken and current will flow. Current will flow. And that's where it is important. Okay. So if I have to show you the characteristics curve of photodiode, characteristics, something like this, only reverse bias. So when there is no light intensity is 0, no light intensity, it's called dark current. This current is called dark current. When light of suitable intensity is falling, as the intensity increases, even the strength of the current also will increase. So if I call this as I1, I2, I3, surely I3 is having more intensity than I2 than I1, because the strength of the currents are increasing. This is photodiode. Solar cell, all of you know. Okay. Solar cell doesn't require an external cell, whereas photodiode requires an external cell. I don't know whether I have drawn it that time. This is your solar cell. Oh, sorry, PN photodiode. It should be reverse biased, I said. No. And there is a glass window. But solar cell, that itself is a cell. It's a PN junction, but acts as a cell. Doesn't require an external cell. And light energy gets converted into electric energy. Okay. Construction and other things are there, but then it is not so important when it comes to our CET. So transistor. Next topic, and I would like to finish this as well in another 5 minutes. Transfer resistor, this is. So this is to be transfer resistor. It is actually transferring resistance, no, transferring electrons from low resistance to high resistance region. So this is the principle behind amplification. Remember, to get amplification, you must push the electrons from low resistance region to high resistance region. Now, how do we get low resistance region? If you forward bias. Forward bias, low resistance always. Reverse bias, high resistance. That's why in transistor, there are two junctions, okay? One has to be forward biased, one has to be reverse biased. Then only push electrons from forward bias region to reverse bias region. Then only you can get the application of transistor, that is amplification. If at all, if anybody wants to know in simple ways what is amplification, very simple. In transistor, which is a two junction device, N, P, N. So P material is sandwiched between two N materials. It's called NPN transistor. Here is one junction, no, junction 1, junction 2. So forward bias the junction 1 and reverse bias junction 2. Simple. You can get the amplification. If you don't do this, you will not be able to get it at all. So then you may ask, if I forward bias both the junctions, what will happen, sir? And also there is something. It will act as an on switch. Transistor can act as a switch, and the most beautiful thing is it acts as an on switch when both its junctions are forward biased. If junction 1 is forward biased, that is this junction is forward biased. You know what is forward bias, no? Connecting N to negative and P to positive. That's forward bias. And if this one is reverse bias, then it is amplification, I said. Amplification. This is on switch. If both are reverse biased, if both the junctions are reverse biased, as I write here, that means here connect to this way. N to positive, P to negative, P to negative, N to positive. This is both reverse bias. Then it is acting like an off switch. So which means transistor can act as a switch as well as amplifier. When transistor acts as an amplifier, when it's emitter, this is emitter region, this is base region, and this is collector region. When emitter base junction is forward biased, emitter base junction is forward biased, and collector base junction is reverse biased. Then it can act as an amplifier. When it acts as a switch, when both these junctions are forward biased or reverse biased. But never we should do the other one. Which one? Emitter base junction reverse bias and ask for an application. No application is there. And collector base junction is forward biased. If you keep it like this for a long time, your transistor only gets spoiled because you've done the biasing to destroy the transistor. Because transistor has not equal doping and equal size for all these three regions, emitter, collector, base. So you should never do this inverse mode. So no application because of this. So very clear, therefore, in transistor we have two junctions, and the two junctions are to be appropriately biased depending on the application. If the application is to amplify, then which kind of biasing we need to do? Emitter base junction should be forward biased, collector base junction should be reverse biased. If you want it to act like a switch, in switch again there are two switches, on and off. You know what is on switch and what is off switch, no? On switch means current is maximum, voltage across the switch is minimum. Off switch means current is minimum, but voltage across the switch is maximum. Your switch in the house also, same thing. But of course, don't think that transistor, that is a mechanical switch. This is electronic switch. Transistor can act as an on switch as well as off switch. When both the junctions are either forward biased or reverse biased. Both forward biased, on switch, both reverse biased, off switch. Logic gates. The gates which, do some logic. Gates are nothing but circuits, okay, electronic circuits. Don't think that they are all made up of diodes and transistors and resistors. Resistors are always there. Diodes and transistors. All these components are connected together to make an electronic circuit, which is a gate. So the electronic circuit which performs some logic is called a logic gate. The logic gate can have one or many inputs, but a single output, no? Single output. So this is the symbol of a AND gate. This is a symbol of a OR gate. And NOT gate is the only gate which has a single input and single output. These are called basic gates. Then we have two more gates called universal gates, using which the remaining gates can be constructed. And that is nothing but to AND, no? You should add at the output NOT. So bubble. NOT is this actually, but I avoid this, only bubble. So this becomes your NAND gate, not a AND gate. Similarly, this is OR gate. You bubble it, then it becomes a NOR gate. So these are called universal gates. Then there are two more gates called exclusive gates, XOR, or simply write XOR plus, or XNOR, or just night plus X. These are all exclusive gates. Symbol of that also can be written. This is a symbol of one more curve should come here. This is one. I will ask you to name it. One more here. This is OR. With one more line, it becomes, if I give it to name, then it is difficult. No? XOR. Whereas this is NOR, no, already, and this one more. This becomes XOR. Okay, these are the logic gates that we have. And yeah, you know, maybe what is OR logic, what is NAND logic, what is NOT logic, all that. It's very simple. By the name only we can make out, no? For example, if I have to write for two inputs A and B, both inputs can be low. Low means connected to 0 volt. Or one can be connected to 5 volt. 5 volt means logic 1, 1, 0, 1, 1. Output is called truth table, okay? Output of OR gate, if I have to write, it will be this way. Output is high. High means high voltage. If any one of the input was high, A or B, that's why OR gate. AND gate. Output is high if A and B is high. That means for 1, 1 only you can get the output 1. Remaining it should be 0. And for NOT gate, it is a different output is not the input. No. If input is 0 volt, output is 5 volt. If input is 5 volt, output is 0 volt. This is NOT gate. So you can think of a NAND. NAND is not AND. No. Not AND means what it should be. It cannot be 0, 0, 0, 1. It has to be 1, 1, 1, 0. Similarly, for NOR, it cannot be 0, 1, 1, 1. It has to be 1, 0, 0, 0. So this is your logic gate. I think that I will stop. If I have any questions, I can take. Any questions? So, anyone is there? From KSTA, post. Swati, you have any question? These are all, Logic Gate is a book. Here it's only one page. Similarly, Transistor is a book. As you study further, your engineering or higher studies. So we introduce only little in PUC level to give you to find out whether you are interested in pursuing the studies in these topics further. So everything is introduced at the PUC level. Remember, this becomes the base to study, either computer science or electronics further. The entire computer science is based on logic gates, correct? Entire computer is built using logic gates, and the remaining electronics that we study, right? So without the logic, there is no program, right? Logic is the heart of the computer program. So we try to develop all these interests in the PU level so that you will pick up these topics in future. I'm done. If there are no questions, I think we can wind up.
So chat box ಅಲ್ಲಿ ಯಾವುದೇ questions ಇಲ್ಲ sir. Later on I sent through my email sir.
Sure, sir. Sure. ಏನು ಕ್ವಶನ್ ಇದ್ರೆ ಕಳಿಸಿ ಸರ್ ಆನ್ಸರ್ ಮಾಡ್ತಾರೆ.
Okay sir. Anyway, thank you sir.
Yes, sir.
I would like to thank immensely for delivering a very good, informative and insightful talk And today's topic, ಮಕ್ಕಳಿಗೆ ಬಾರಿ ಸುಲಲಿತವಾಗಿ ಈ ಒಂದು ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮವನ್ನ ಬಾರಿ ಸರಳವಾಗಿ ಹಲವಾರು ಉದಾಹರಣೆಗಳ ಮುಖಾಂತರ ತಿಳಿಸಿಕೊಟ್ಟಿದ್ದೀರಾ ಸರ್. So on behalf of KSK and myself,
Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you.
ಹಾಗೂ ಇಂದು ಹಾಜರಾಗಿದ್ದ ನನ್ನ ಎಲ್ಲ ವಿದ್ಯಾರ್ಥಿ ಮಿತ್ರರು, ಸಹೋದ್ಯೋಗಿಗಳು ಹಾಗೂ ಅಧ್ಯಾಪಕರುಗಳಿಗೂ ಕೂಡ ಧನ್ಯವಾದಗಳನ್ನು ತಿಳಿಸುತ್ತಾ ಈ ಒಂದು ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮವನ್ನು ಮುಗಿಸುತ್ತಿದ್ದೇವೆ. ನಾಳಿನ ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮವು ಎಂದಿನಂತೆ ಸಂಜೆ 4 ಗಂಟೆಗೆ ಆರಂಭವಾಗಲಿದ್ದು, ವಿದ್ಯಾರ್ಥಿಗಳು ಹೆಚ್ಚಿನ ಸಂಖ್ಯೆಯಲ್ಲಿ ಹಾಜರಾಗಿ ಸಂಪನ್ಮೂಲ ವ್ಯಕ್ತಿಗಳು ಕೊಡುವಂತ ಪ್ರಶ್ನೆಗಳಿಗೆ ಉತ್ತರಗಳನ್ನು ನೀಡುತ್ತಾ ತಾವು ಹಾಜರಾಗಬೇಕೆಂದು ನಮ್ಮ ವಿಜ್ಞಾನ ಮತ್ತು ತಂತ್ರಜ್ಞಾನ ಅಕಾಡೆಮಿ ವತಿಯಿಂದ ತಿಳಿಸುತ್ತಿದ್ದೇವೆ. ಎಲ್ಲರಿಗೂ ಧನ್ಯವಾದಗಳು. ಥ್ಯಾಂಕ್ ಯು. ಥ್ಯಾಂಕ್ ಯು ಸರ್.
Thank you, sir. Thank you. Pleasure.